Hi, I'm Jacob Andreas. I'm an assistant professor at MIT and EECS and CSAIL, and I work on natural language processing. So sort of broadly, my group is interested both in developing better technologies, better machine learning models for working with data from human languages, and looking at what we can do with language in support of other kinds of artificial intelligence applications. Doing things like building robots that you can teach using natural language, or computer vision systems that can explain their decisions also in language. And today I'm going to be answering your questions about large language models. What are large language models and how do they generate text? When you're typing on your phone and you see that little sort of line that pops up with some guesses about the word that's going to come next, that's a language model. And sort of fundamentally what most of the language models that we work with are just predictive models of text, models that have been trained on enormous amounts of text data to look at a sentence or the beginning of a sentence or look at the document in the beginning of a document and just predict what words are likely to come next. How are LLMs, large language models, trained? Sort of building on that previous answer, the big difference between a large language model that you might have heard of, like GPT-3, and the language model that sort of sits there doing predictive text on your phone is really just the scale of the data that it's been trained on. And the biggest models that we have right now have really been trained more or less on most of the text on the internet. They're sort of enormous machine learning models with really, really high capacity that have just been sort of trained to do that same next word prediction task, but on a much, much, much broader diversity of documents, set of kinds of text, languages of documents, and so on, than the one that sits on your phone. What are some of the key technical innovations that have enabled the development of large language models? So language models, it's important to note, have been around for a long time, really since the very earliest days of natural language processing. So when people were first setting out to build automatic speech recognition systems, really sort of at the dawn of computer science, there was always this problem of figuring out, well, if I have a couple of different ways of interpreting the audio that I'm hearing, which of those is actually likely to be the sequence of words that people meant? And even then, people sort of trained these kinds of predictive text models that could look at a sentence and guess what word was coming or tell you whether a sentence was likely or not. And so these have been with us for a very long time. And the reason that I think most people are hearing about them now, or the big thing that's sort of different in the last 3 or 5 years, is just sort of how much bigger and how much better these models have gotten. One of the key drivers there has been the sort of widespread use of artificial neural network machine learning models as models for language processing. These have also been around, really for a long time, like since the 60s. But various developments have kind of converged in the last couple of years that means that we're able to train them at a very large scale, we're able to train them on a large amount of data, and they just work super, super well. And so what we're seeing with sort of large language models today is a sort of convergence of better hardware for training neural network models, some basic innovations in how those neural network models are trained, and then just enormous amounts of data on the internet that allows us to train them at a really large scale. How do language models differ from traditional approaches to natural language processing? So maybe one of the other biggest differences between these models that we're seeing right now, and even the kinds of language models that people were building, when I was in graduate school not very long ago, is that we bake very little about the structure of natural language into them ahead of time. And so, it used to be that a large part of the work in natural language processing was sort of taking our understanding of how languages are structured, how, sort of syntax works, how the morphology of individual words work, and building that into specialized machine learning models that could use this information to make better predictions. And with many of the kinds of models that we're training right now, you don't necessarily have to bake all of that information in from the beginning, and instead these models learn just from reading training on large amounts of data, what the structure of language is and how it works. Now, this is not to say that sort of knowledge about linguistic structure is not useful for NLP. It's certainly the case that in languages without large digitized training sets or with small numbers of speakers, being able to build models that really do have access to sort of rich information about linguistic structure is still important. And our understanding of how language works can inform the ways in which we test these models to make sure that they're working, and the ways we sort of probe their internal representations to figure out how it is they work. But I guess the biggest difference between the way we're doing things now and the way we were doing things even 5 years ago or 10 years ago is that most of that structure sort of gets used after the fact and not when we're training models from the outset. What are some of the challenges involved in training and deploying large language models? And maybe the biggest challenge, which I've been alluding to a little bit already, is just the fact that these models require huge amounts of computing power to train. And so nowadays the kinds of models that you've heard about, things like ChatGPT or Llama, have been trained on hundreds or thousands of GPUs for hours and hours and hours and hours. And this presents a couple of different challenges. It both just requires an enormous amount of energy to train these models. The training process itself is complicated. It's sort of the idea of training a machine learning model at this scale or at this for such a long time is not something that we've done until relatively recently in the machine learning world or in the natural language processing world. And so a lot of the challenge really comes in training. And I think this is part of the reason that there are only a small number of these models out there that sort of most people are interacting with or that most people have heard of, because training even one of them is just like a really complicated and really costly endeavor, requiring huge teams of people and hundreds of thousands or millions of dollars. And as a result is the sort of thing that people are only doing relatively infrequently. Why do the most prominent large language models all have effectively the same architecture? And what is the architecture of a transformer model? Many of the biggest language models that we're sort of seeing released to the public right now are based on a particular neural network architecture called the transformer that was introduced around 2017. And the way a transformer works is basically you sort of take a chunk of text as input, whether it's a sentence or a paragraph or a document, and you look at individual words or sometimes pieces of words in that document, and you represent them as actually points in a very, very high-dimensional space. You then apply a series of operations that are called attention to those points, where every point sort of looks at all of its other neighbors, decides to wiggle itself around a little bit in that space, and then all of the neighbors do the same thing. And you repeat this process over and over and over again, till eventually you sort of take one of those points, you figure out which word it's now closest to, which is probably not the word that it started out closest to, and that becomes the model's output at the next time step. These transformer models are not the only way to build a language model, or even a neural network-based language model. And one of the reasons that I think we're seeing such a dominance of this kind of transformer architecture in the last couple of years is that they're really easy to train at a large scale. And so I mentioned before that these sorts of computational constraints are one of the big issues or the big challenges that come up when training these language models. And these transformer-type models turn out to be particularly well-suited to training in a distributed way, training at a large scale. And I think that's one of the reasons that we've started to see so much of them right now. But it's important to mention that that's not the only way to build a language model, and it wouldn't surprise me if in the next couple of years we actually start to see greater diversity in the kinds of neural language models even that people are training. What are some promising ways to use these models, and especially ways of using these models beyond the language and code applications that many people have seen? Taking a step back, right? Why are we here? Why are we doing this explainer? Why is there so much interest in language models in the first place? And I think a big part of this is that, starting with this very simple task of predicting what word is going to come next in a document, turns out to give models that are capable of accomplishing a wide variety of other useful things, right? So, sort of mentioning ways of language or using these models in the context of language applications. If I'm trying to write an essay and I, type in a question or a prompt that says something like, what were the causes of the First World War? A good guess at what kind of language is going to come next, if you're a good autocomplete model, is an essay or is a sort of detailed answer that actually addresses those questions. And what this means is that a lot of things that we haven't sort of traditionally thought of as things that language models are for, or even things that are kind of within the domain of natural language processing as a field to tackle, you can actually pose as these kinds of next word prediction problems with appropriate prompts. And what this means is that we can use these language models to do a ton of different things. And so as the question gets at, a lot of the applications that people have seen so far really build directly on this kind of text autocomplete paradigm, right? You're sitting in your text editor in your Microsoft Word or Google Docs, you type in some instructions or you type in the sort of beginning of a document and you ask the model to guess what's going to come next. And sometimes that's the text, or at least close to the text that you already wanted to write. And similarly, in these kinds of programming applications, right, you type in a comment, and if you have a really good model, that model can often guess what code should come after that comment, especially if it's really, the sort of boilerplate code that many of us find ourselves writing over and over again, that we know other people out there have already written many times and maybe even posted in versions that exist on the internet. All that said, I think we're likely to see these models showing up in all kinds of other interesting places even in sort of problems that on the surface maybe seem not to have anything to do with text or anything to do with programming at all. So one thing that my group, for example, has been thinking a lot about recently is what we can learn from text, or what we can sort of extract from language models about how the world works in a general way that we can then use to support computer vision, or sort of improve models for robotics or models for computer vision, right? So if you're trying to accomplish some sort of difficult household task, cleaning a room, cooking a complicated meal. There's a lot of common sense knowledge that's sort of difficult to get from traditional robotics or computer vision training sets. What kinds of objects are likely to co-occur together, what a sensible place in your living room is to set down this pillow that you just picked up, where in the kitchen you're likely to find a teapot or tea bags or things like that. And what's amazing is that language models, again, just by sort of virtue of doing this next word prediction task, know a lot of these things as well. And so if you query them in the right ways and at the right times, you can actually use them to fix or improve or guide the outputs, even of models for like robotics tasks and computer vision tasks, where there might not actually be any language as an input or as an output to the model. How do multilingual transformers handle different languages and dialects? One other thing that we're starting to see in the models that people are training right now, or at least in many of the largest scale models, is that they're trained not just on a single language, but on many, many different languages, maybe as many different languages as we can get our hands on. And this is a really important development. For a long time in the history of natural language processing as a field, a lot of the research was being done just in English, sort of building models that were trained only on data in English, or even that worked only on English, even if you tried to train them on other data sets. Now, this is certainly not what everybody's been doing, and there's a long sort of history going back to the earliest days of the field of trying to do NLP for other languages. But if you just look at most of the papers that are getting published at our sort of top NLP conferences, a lot of the work is in English. And so one thing that we see when we train these models on multilingual data is that not only do they sort of acquire the ability to do all of these impressive things, not just in English, but in other languages as well, but that actually you often benefit, especially in the smallest languages, by sort of training models at this large scale. So there's a sense in which models can sort of take skills that they acquired from tasks that were specified in English in the training data and can generalize those to languages that maybe were sort of so sparsely represented in the data that they don't have examples of every individual task that a model is solving. And so, I guess an important feature of these multilingual transformers is just that they, not only can they handle different languages and dialects, but that they get better, especially at those sort of least represented languages and dialects as these scales get bigger. Now, an important caveat there, of course, is that our performance with these models in English is still far ahead of most of the other languages that we can train them on. There's still enormous need for technologies that serve people that are not sort of speakers of the world's five most frequent languages, or users of those languages. And while these multilingual models are an important first step in that direction, I think there's still a lot of work to do, both on the modeling side and really especially on the benchmarking side, just to give us a kind of clear picture of how well these tools work outside of English and especially in less common languages. What are the limitations of large language models, and how can they be addressed? This is a big question, and I think one of the most important ones is what we were talking about just a minute ago with regard to sort of how well they work in different languages, and even just understanding how well they work for different kinds of users. But there are also, sort of user-specific questions aside, a couple of like really fundamental issues that even the biggest models that we have today still face. One of them has to do with factuality, right? So it's well documented that these models hallucinate facts, that they're not always reliable. I can't remember why I was doing this, but recently, asked ChatGPT to, describe some of our group's research, and it, named 5 papers, 4 of which are not papers that actually exist, and one of which is a real paper that was written by a colleague of mine who lives in the United Kingdom, who I've never co-authored with. So factuality is still a big problem. And even sort of beyond that, things involving reasoning in a really general sense, things involving sort of complicated computations, complicated inferences, still seem to be really, really difficult for these models, and might be even sort of fundamental limitations of this transformer architecture, and are, I think, somewhere where a lot more modeling work is needed to make things better. Can large language models understand context? Also an interesting question, and I think depends on a lot on what you mean by context. So certainly when we think about linguistic contexts, these models are capable of sort of reasoning about much, much longer documents, and, sort of chunks of text more broadly, than really anything that we've known how to build before. But that's only one kind of context, and sort of in people, right, language production, language comprehension takes place in a sort of grounded context, right, that I know I'm sitting at this table, there are objects that I can refer to, and the language models that we have right now, when they're interacting with a human user, typically can't see any of that. There's a broader social context that informs a lot of our language use, and also that these models are at least not sort of immediately sensitive to, or where it's not clear how to give them information about the social context in which their language generation and language modeling takes place. Another important thing is, I guess, temporal context, right? That we're sort of shooting this video at a particular moment in time when particular facts are true. The models that we have right now, we're sort of trained on a snapshot of the internet that stopped at a particular time. For most models that we have now, probably a couple of years ago, and they don't know about anything that's happened since then. They don't even know sort of at what moment in time they're doing text generation. And so figuring out how to provide all of those different kinds of contexts is also an interesting question.